My name is Roy Keyes. I'm a data scientist, but I used to be a physicist. And my background is in medical radiation physics, and when I once upon a time did a PhD, it focused on computational methods related to medical physics. I've been a data scientist since 2012, mostly working with tech startups, and nowadays I work at a company called Arundo in Houston, and we're building a, quote, industrial IoT data science platform. So if that sounds interesting to you, we are hiring. You can come talk to me. I'm a long-time Python user, done lots of work in sort of scientific and engineering-related stuff in Python since the early days. And today I'm going to talk about something that is, it's actually a personal side project unrelated to my official work at Arundo, but I hope you find it interesting. The outline is basically, I'm going to give background on radiation therapy since I assume this audience isn't super familiar with it, and the dose estimation problem. And then I'll talk about the machine learning approach to this and then go over some of the results and a little bit of the future work I'm hoping to do. So radiation therapy is the use of ionizing radiation to treat disease. Ionizing radiation typically means we're talking about high energy X-rays or high energy photons like X-rays and gamma rays, or charged particles like electrons and protons, or also sometimes neutrons. And when we talk about disease, that typically means cancer, but sometimes there are also benign diseases that you will treat with radiation. And the reason why you would want to do this is because radiation is more locally targeted than things like standard chemotherapy, and then on the other hand, it's less invasive than surgery. And it's actually super duper common. It's used in about 60% of treatments for cancer in the US. So you see it all the time. There are two broad categories of radiation therapy. The first one is the one I'm going to focus on more today, but it's when you use an external radiation source. It's called external beam therapy, and that means usually you'll have a particle accelerator, and it's generating a beam of electrons or X-rays or protons. Or you could also have a machine with a big radioactive source like cobalt-60, and you collimate the radiation coming out into a beam that you can use on a patient. The other very common way to deliver radiation therapy is internally delivered, and that's called brachytherapy. And basically that means you would take a radioactive source or a miniature X-ray tube or something and put it right in the tumor as close as you can as possible. A little bit more invasive. And the goal of radiation therapy is to deliver a dose of radiation that will kill the target cells. That basically means the tumor, but at the same time you want to spare the healthy surrounding tissue and organs as much as possible. So you can see this absolutely idealized diagram. Basically you've got your tumor, which is the smaller green square, and then you've got surrounded by healthy tissue. What you would really like to do, the ideal scenario is that you have this prescription radiation dose that would be right to that target and then nothing around that. But as you might imagine, that in the real world things are a little bit trickier, and even if you use very advanced techniques like proton therapy or carbon ion therapy, you always get some spillage outside of your target volume. So I'm going to talk mostly about this external beam therapy today, but the problem that you face when trying to plan radiation therapy is that you're trying to do what we just said, which was get that target dose to the tumor target and then deliver as little as possible outside of that. So typically what that actually means is that the radiation physician will go in and define the target area, which is a volume. They're usually looking at a CT scan of a patient, and then they'll say, this is the dose we want here, and then they'll also define some other structures outside of that. So you can imagine if you were treating for breast cancer, for example, which is one of the most common cancers, you do this, you want to spare the heart and the lungs, and so usually they'll put sort of thresholds. This is the maximum amount of dose that can go to those organs. And then you've got a bunch of parameters for the beam you're shooting in. So this is where your optimization problem comes in. You've got the angles that the beam might come in. You've got the shapes that you can shape the beam, and then also the fluence of the beam. Basically, how long do you turn on the beam given a different angle and shape? And so you have this very large parameter space, and what you're going to do is look through all those different parameters and try to come up with parameters that will give you a dose distribution that is as close as possible to your desired dose distribution. And that then involves hundreds or thousands of dose calculations. And that's kind of where this comes in, is that your plan is only going to be as good as your dose calculation. So you need it to be very accurate, but also you need to be very fast so you can iterate through all of these different parameters. The gold standard for doing these kind of radiation dose calculations is a physics-based Monte Carlo. So basically that means you are doing micro-scale physics simulations, or depending on how you define micro, we'll say small scale, very small scale. And that means what you're doing is you are tracking a single particle of radiation, and at each step you are doing your Monte Carlo, which is pulling from some distribution and deciding what's going to happen next. Now, those distributions are very well known from fundamental physics. People do laboratory physics, and that part is very well understood. So what that means is you can do these Monte Carlo calculations, and they are very, very accurate. But because you need to do this millions of times to be able to build up a distribution, it turns out to be very slow. And in the clinic, they don't do this very often. It's very uncommon to do sort of a full Monte Carlo to get the most accurate calculations. What they end up doing is a trade-off between speed and accuracy. So you kind of can ride down some curve of how accurate do we need it to be versus how fast we need it to be. So this is something that I've worked on, these kinds of problems when I was a graduate student. And so something that I've always been thinking about is where can you get sort of on this curve, can you move this curve of accuracy versus speed? And so more recently, after I'd been doing a lot of machine learning, I thought, maybe we can pose this as a machine learning problem. And the sort of setup for that is that we can do slow but accurate calculations, but we really need fast calculations, and we would like them to be as accurate as possible. From a machine learning perspective, we can get inputs and outputs. The inputs to this would be the beam parameters and the geometry and composition of the target, or the medium, which is in this case a human being, which you're going to get that information from a CT scan or an MRI scan, depending on what you're doing. And then the output of your calculation, of course, this dose distribution. So the question then is, could we use a machine learning model to essentially become a physics black box and give us what we wanted, which was accurate enough dose distributions and hopefully faster? So the interesting parts then become, we kind of have access to an unlimited amount of training data that's arbitrarily accurate. Of course, it's not free because we need resources to do this. So you're looking at maybe potentially CPU hours per training example. But that also means that we can get maybe arbitrarily accurate in what we're doing depending on our resources and sort of appetite for how much training data we want to do. And of course, there's a lot of stuff around our algorithm choice and all those things. As the approach that I was using for this is essentially to go from simple physics scenarios to more complex ones that get closer and closer to something that is like a clinically realistic scenario. So first, before I get into what I was actually doing, I'm going to talk for a moment about proton therapy and proton doses, because that's the simulations I was using. But I have my little fake pointer here. When you do external beam radiation therapy, one of the things you'll look at all the time is something called a depth dose curve. And basically, what that means is here you have on our bottom axis, you have the depth. And this is how deep into a medium you're shooting your beam. And then on the y-axis over here, we have the dose that is deposited at that depth. And basically, you can imagine that if our plot was, a person or something, and we would have the target tumor somewhere in there, and we want to put our beam in to get the dose we want at that depth. So that comes up all the time. The proton beams have a very characteristic depth dose curve called a Bragg curve. And the interesting thing about it is that at the shallower areas, you have a relatively low dose, and then it has this so-called Bragg peak where you have the highest dose, and then it basically drops off to nothing. And this is in contrast to X-rays, which are the most commonly used form of external radiation therapy, which have essentially like an exponential drop-off, so that the shallower regions get a higher dose than the deeper regions. So that's one of the things that makes protons interesting. Of course, they are much, much, much more expensive to actually do. But the other interesting thing is that the location of this Bragg peak is based on the initial kinetic energy of the beam. So you can kind of dial in where the highest dose is. So that makes it a very interesting kind of thing. And this occurs with any charged particles that are heavier than electrons. So protons are the most common form of this, but you can use other sort of heavy particles. Heavy is a relative term here because these would be considered light particles by other physicists. So I started off with the simplest scenario, essentially doing a 1D dose calculation. And in this case, what I was doing was using a 100 MeV proton pencil beam, shooting it into a box of water. Well, this is, of course, an in silico digital box of water. And to make it a little bit more, slightly more realistic and interesting, I introduced an air pocket. And the air pocket is important just because a real medium, which is going to be a human or something, has many different densities and all sorts of things that you have to deal with. And that's one reason why you need very accurate calculations, because that can change the distribution of the dose in the end by in important ways. So basically what I did was in this 1D example, I put in these air pockets and then I moved them around and I created hundreds of training examples. And this was basically the very first proof of concept. And then what I did was I went to my scikit-learn, import that, and I trained gradient boosted trees. Originally, I actually tried random forest in the very beginning, but that was turned out to be a bad choice. But gradient boosted trees, which is does a lot of stuff. If you're familiar with that, it's good at handling a lot of specific scenarios. I went with that, and basically I do a search on the hyperparameters, tune those, and then I ended up with something that looks pretty interesting. So this is another one of these Bragg curves, and right in the middle I have this little divot, which is where the air pocket was. Now in this plot, it almost looks like there's just one thing, but there's actually two plots. The blue in here is the Monte Carlo, and then the green is the gradient boosted trees here. And you can see that these curves lie essentially on top of each other. So this was the first sort of proof of concept. There's a slight deviation here where you get a little bit of backscatter around this air pocket that the model was unable to pick up. But otherwise, it's very accurate. And I'll talk a little bit about that when we get towards the end. The next iteration on this was around two-dimensional dose calculations. And in this case, it's a very similar scenario. This one is a little bit, this previous one we saw was a very high resolution, 0.25 millimeter bins, just to see the exact structure we'd see. This one is a lower resolution, 1 millimeter bins, but this is actually what's used clinically. This is actually considered high resolution. In this one, you can see there are a couple different air pockets here. And the way this one worked is I put in two air pockets that were actually half of the plane here. This is basically like a little plane with some, it actually is 3D, but it's sort of, we consider it's 2D. And moving these air pockets around and then seeing if I could use that to train up this algorithm. So this is, that's what this looks like. This is actually from a holdout set that was not used in the training. And then this is what it looks like when we used boosted trees. And in this case, I actually used XGBoost, the Python interface to XGBoost, which is of similar accuracy to the scikit-learn one, but it's just a lot faster to train because of several things they've implemented. If you see here, these look pretty similar. In fact, the main difference you'd see is probably up here in the title. It goes from MC to ML. But also, you can't really see those little air pockets as well. They didn't get picked up quite as well. Here's side by side, and then I'll show you the differences here. If you plot these on the same scale, it's kind of hard to see the differences, which is a good thing. Here I've used a diverging color map, and anything above in the reddish region is a positive difference. Anything in the bluish region is a negative difference. But it's hard to see where the differences are. If I kind of change that scale a little bit, you can see the location of the differences, but they're actually very small. In the clinical medical physics world, this is a super common scenario, is you are comparing these dose distributions. And I'm not sure how common this is in other fields, but essentially what you're doing is you are comparing a geometric point distribution of a quantity. And basically what you're doing is, you can imagine like comparing two photographs to see what's changed. That's a very common scenario, is to look at these distributions. And so versus a more common thing that data scientists or other people, other scenarios you'd run into where you're looking at a point estimate versus a distribution to see if they match up. But this is actually a series of points. You're just comparing point A to point B. And so in medical physics, they have several kind of domain-specific tools, and one of the most common ones called the gamma index, which I don't expect any of you to have heard of unless you're actually a medical physicist. But I'm going to go over that real quick without detail. But essentially, the gamma index is a way to look to see if two distributions have shifted up into some threshold. As you can imagine, that's very common with equipment moving and that kind of thing. You have a misalignment. And then the other one is just looking at the absolute difference in the values. So we'd say it's like displacement versus just a dose difference in the point. And typically you say you'll have some threshold. Is it more than X millimeters displaced a single point, or is the single point more than Y% difference of what we expect? And I won't show the actual sort of algorithm to do that because it requires a lot of explanation, but basically you end up with a value, and if it's 1 or below, it's considered good. Above 1 is considered bad. But what you typically do, because this is this geometric distribution, is you say, oh, what percentage of our points have passed, and then you say if you have more points at some threshold that have passed, then you consider the whole thing good. So this is a 2D plot of the gamma index, and basically I've again chosen a diverging color scheme here so that anything in the bluish region is good and anything in the reddish region is bad. And as you can see also, well, I've also plotted as a histogram. And basically we see that everything turns out to be good, so all is good. So very happy with that. So far, basically, the things that I've done, we've seen the accuracy is acceptable. Maybe it's not as good as maybe we would like yet, but it's sort of acceptable in these these early studies that I've done. But the most exciting thing is probably the speed. So the 2D version that I did, the speed ups we were getting over a full Monte Carlo is about 50,000 times speed up. And I made several changes when we went into the 2D about the resolution and the size of the gradient boosted tree forest that I was using, and several other things. And in that case, I a little bit unexpectedly got actually a higher speed up, so about 200,000 times speed up. Those sound like big numbers, and I think they are. As far as I know, the state of the art for doing this kind of calculation with acceptable accuracy is about 500 times speed up, maybe 1,000 times speed up. So that's all very exciting. You can tell I'm excited. But there's a lot of caveats. That's why I'm not going out there and telling you to buy stock in my personal side project. But there's a lot of caveats around this. I mean, we haven't gotten to the point well, I'll tell you what that means in a second. We haven't gotten to the point where we're using very clinically realistic scenarios, and then benchmarking is hard. That's just something in general. It's a hard thing to do. You need to evaluate lots of different scenarios. But basically, so this is a presentation of this future work. I think this is very interesting because we're really looking at a physical system and we're doing this data-driven, essentially black box approach, but it still seems like we're getting good results. The future work that I'm planning to do is clinically realistic 3D scenarios. So we're reading in CT scans and doing essentially what you would do in a clinical scenario to do this, and then directly comparing it to these clinical systems. And the we I mentioned earlier is that I've started this collaboration with some people at McGill University. So me as a former academic I will now hopefully have some grad students working on my stuff, which is exciting, especially not having to do grants. But I'll just talk about real quick some of the tools we use, a number of other tools that are like for the Monte Carlo and everything, but also the Python tool is sort of the typical scientific or data science Python stack. And then a couple of tools that are specific to medical physics. So there's some medical physicists come up with this nice library called PyDICOM to handle medical images. DICOM is a very standard medical image format. A long time ago, I did some work on that. but I haven't been working in this area as much until I came back to this project. And then another one, the gamma index I was talking about, which is sort of non-trivial to implement. There are a couple packages, but I used one called NP gamma to do that. And then I'll sort of leave this little one-slide summary, which is basically, like I said, we've got a physics problem. We can do very nice, highly accurate calculations, but they're very slow. And in the applications we'd like those to be much faster. But of course, we would prefer to maintain as much of that accuracy as possible. And then in this research, I just recast that as a regression problem using machine learning. And so far, the results have been very encouraging. So I think that I'm done even a little bit early, so I'll take lots of questions, I guess. Or none, I don't know. Oh, here we go. Okay, good.
Forgive the ignorance, but in the clinical setting, are they recalculating? Like, could you use Monte Carlo with unlimited computer speed in the clinical setting? Are they calculating in the clinical setting, or are they doing it before the surgery?
So the typical way that this happens is a patient will come in, they've already been diagnosed with cancer, they'll see the radiation oncologist, and then they'll be sent to get like a CT scan, and then the physician goes in and they'll outline the different volumes and set the sort of the targets and the constraints and everything. And then you will put this in as an optimization problem, and like I said, there are so many parameters that you want to go through this huge parameter space, and you need to evaluate the dose from those parameters at each time. So it's just prohibitively expensive to use Monte Carlo. My understanding is, sort of in recent years, the only time they've used sort of what I would consider full Monte Carlo is to do things like after they've decided on the best parameters, they'll just sort of do a double check, because it may take CPU weeks worth of time to get full high resolution Monte Carlo. There's a whole spectrum of algorithms they do use for these dose calculations, and some of them you could be considered like modified Monte Carlo and everything. And then the most common one, which is very fast, is what we call dose kernel methods, where essentially you use Monte Carlo to calculate a dose distribution, and then you will use those for a few different scenarios and do sort of this convolution over your geometry and essentially distorting these kernels to get an estimate. But they don't work nearly as well on a lot of these situations, especially for protons, which have those very fine peaks, and when you have heterogeneities, because you might see anything from air to water to muscle to bone to titanium implants, and the physics around those are very different. So I don't know if that explained it, but yeah, basically it's very slow. The places that do use the full Monte Carlo, at least in the past, have been places like Harvard, who would have a giant supercomputing center so they can do massively parallel calculations.
So I was wondering, with the speed up that you're seeing, how close your models are to the complexity that you would typically see in like when you're modeling a patient? So.
Okay, I guess I should be repeating questions. The question was, how close are the basically what I'm doing to the actual clinical type scenarios? And so far, I would say we're still at the beginning. I mean, the big problem is that when you start looking at all those, at patient geometries and then the compositions, you have an exponential explosion in your parameter space there. So you could have, you could generate sort of an infinite number of training examples, but it might be a smaller infinity than the possibilities. I haven't done the math around this, but there's a huge parameter space. So when we're doing this future work, a lot of it is around being very smart about how we generate training examples. And it's a common machine learning problem. If you want to look at dogs versus cats, you need to get a very representative sample of what dogs look like and what cats look like. And sometimes it's hard to get there. And in this case, it's the same kind of thing, but we have a continuum of scenarios that we need to try to cover it in a statistical sense of all the parameter space. So far I've done these relatively constrained scenarios. So for example, in that 1D version, I've done actually a few different 1D versions, but they ultimately usually come down to like one parameter difference. In the 1D version, I don't have to feed in excuse me. you don't have to feed in what's the full geometry of the scenario, because the only thing changing is the location of that. When we get to more complicated scenarios, essentially the input is going to be everything, right? And but yeah, I put thought some around what can we do to maybe reduce the dimensionality of the inputs and things like that, but haven't gotten to the point. All right, I think, looks like I'm done. So thank you very much.